We are asked to evaluate the integral, and you are probably completing this question within the context of integration using partial fractions. So that's the technique that we will use to solve this problem. The first thing that we can do is actually take the constant here in the numerator and just factor it to the outside of the integral. So you would have 50 on the outside multiplied by the integral of 1 over your factored denominator. We will notice that the denominator is already factored, so we don't need to do any further factoring. And if we look at those factors carefully, we have a linear factor. And we know this is a linear factor because it's x raised to the power of 1. And then here we have a quadratic factor. And we know it's quadratic because we have x raised to the power of 2. And that's important to note because the way in which we proceed for linear and quadratic factors is a little bit different. So the next step really is the partial fraction aspect of this question. We actually have to take the expression 1 over x minus 1 times x squared plus 49, and we have to rewrite it in a simpler manner, in a manner that allows us to integrate more easily. And we'll do that first, and then we'll come back and actually integrate. So for the time being, we're going to pull out that expression right here and just algebraically simplify it, and then we'll return and do the integration. So for a linear factor, what you're going to do is, in the denominator, you're going to represent that as x minus 1, so you just use the same linear factor, but in the numerator, you will write a constant a, and it is our job to find that constant a. For a quadratic factor, again, you're going to write the denominator, but to represent the numerator, you're actually going to do bx plus c. One way, perhaps, of remembering this is if the quadratic factor has a power of 2, then the factor in the numerator should be reduced to a factor of just 1x to the power of 1. It actually works the same way with the linear. We have x raised to the power of 1 in the denominator. If we reduce that by 1, we would have x raised to the power of 0. So that's one way of remembering how to set up the numerators for each of the linear and quadratic factors. The next thing you have to do is find a common denominator. So we're going to have to multiply this denominator by x squared plus 49, and of course we'll have to multiply the numerator also by the same factor. And then for the other denominator, we need to multiply it by x minus 1, so we'll multiply the numerator by x minus 1 as well. Now that the three denominators are equivalent, you can basically just cross them off. That's equivalent to multiplying each term by the denominator. So now you have 1 is equal to a times x squared plus 49 plus the bx plus c times x minus 1. Now remember, your goal is to find the value of the constants a, b, and c. And there's a couple of ways in which we can proceed here. One thing that I like to do is to notice, because of this x minus 1, if I let x equal 1, and basically what that means is I'm going to plug 1 in for all the x's. When I put 1 into this x, I'm going to have 1 minus 1, which is 0. And if I multiply 0 by this factor here, you get 0. So in other words, this whole thing would cancel out. And then I would also plug 1 in for this x right here. So now I have 1 is equal to a times, and then I'm going to have 1 squared plus 49. This allows me to solve for a directly. So now I have 1 is equal to 50a, and then if I divide both sides by 50, I have a is equal to 1/50th. So that's kind of nice. I've already solved for a. But we have to go back and solve for the other constants as well. And perhaps to do that, we're going to have to distribute the a, and then we're going to have to FOIL this out as well, multiply that out. So if we distribute the a, we'll have a x squared plus 49a. And then if we FOIL this expression out, we will have bx squared minus bx plus cx minus c. Now what we'll do is we'll focus our attention on the terms that contain x squared, so those two terms. Notice on the left side of this equation, there is 0 x squared terms. So you can almost imagine that on the left side you have a 0x squared, and then plus this 1 right here. So the left side has a x squared term as well. And what you do is you set those terms equal to one another. So you set the 0x squared equal to the ax squared plus the bx squared. And then you divide each term by x squared, which essentially cancels it out. So you have 0 is equal to a plus b, And then we already know the value of a, it's 1/50th, so you can plug that in. And then solving for b, you will get negative 1/50th for b. So that completes the solution for b. We just have to find c. So let's go back to this crazy looking equation and see if we can figure that out. In fact, c will be relatively easy to find because what we'll do is we'll highlight the terms that do not contain an x. So these are known as your constant terms because they don't have a variable. So you have 49a and the minus c. On the left side, you have a constant term of just 1. So you'll set those constant terms equal to one another. You'll do 1 equals 49a minus c. Once again, we know the value of a. It's 1/50th. Well, this is going to get fun. So now we have 1 equals 49/50ths minus c. I suppose you could subtract both sides by 49/50ths. And when you subtract both sides by 49/50ths, you're going to get 1/50th is equal to negative c. Divide both sides by -1, and you get negative 1/50th is equal to c. So now we have our a, b, and c. We go back to our original partial fraction decomposition. Why don't we actually rewrite it? So if you recall, we had 1 over the x minus 1 times x squared plus 49. This was equal to a over x minus 1 plus the bx plus c over x squared plus 49. Now we can fill in our a and our b and our c. So this is going to allow us to rewrite the integral in a simpler manner. So recall the a was 1/50th. This is over x minus 1 plus, okay, now in the numerator we have the b value, and the b value was negative 1/50th. And then you'll have x, and then we're going to add c. Our c was actually a negative 1/50th, so we'll actually have minus 1/50th right there. And there is the way in which you can rewrite the integral. So now we're going to actually perform the integration. We can scroll back up and recall that our original expression looked like this. So let's copy it. Recall that we had factored out the 50. So we'll have to keep that in mind. So we now know that this integral can be rewritten as 50 times, and then this expression right here. So why don't we just copy and paste it? There we go. And at the very end of the expression, we'll throw in a dx for notational purposes. In fact, it's probably easier now to send the 50 back through. So to multiply the 50 back in will actually make our fractions become a little unfraction-like. So 50 times 1/50th is just 1. So you'll be back to 1 over x minus 1. What else can we do here? In fact, let's tweak it a little more. We have this minus sign here and here. So if we factor out a negative, we could put it right there. Those terms would then change to positives. So that's kind of nice. And then 50 times 1/50th is just 1x. And then again, 50 times 1/50th is just 1. So basically you'll have x plus 1. And then this will be over the x squared plus 49. So it's looking a little bit nicer. But we can do even better here. For this second term right here, what you'll often have to do is split that up into two separate fractions yet again. But you don't have to go through partial fractions. You're going to have 1 over x minus 1 minus, and then you'll put the x over the x squared plus 49, and then plus 1 over x squared plus 49, like so. So now you have 3 expressions. It's a 3-for-1 special, and you have to integrate each one of them. 2 of them would be amenable to u substitution. This one, we'll do it real quickly. You could let u equal x minus 1, differentiate both sides to get du equals dx. So then you have the integral of 1 over u du. And then if you integrate that, of course, you get the natural log of the absolute value of u. And then putting your u back in gives you natural log of absolute value of x minus 1. So that one's done. This one can also be evaluated using a u substitution. Let's let u equal x squared plus 49. Differentiate both sides to get du is equal to 2x dx. Personally, I like to solve for the dx, so I would have du over 2x is equal to dx. Then I rewrite my integral. I would have the integral of x over my u, and then times my dx, which was du over 2x. What's nice about this is these x's would cancel out. So we'll cancel those. We still have a factor of a half that we can pull out. So now we have 1/2 integral of 1 over u du, which again is just ln of absolute value of u. And then if we put our u back in, we have 1/2 ln absolute value of x squared plus 49. So that one's done as well. The third one is a little trickier. This one is going to be an inverse tangent. There's actually a little rule of thumb that many of us have learned that when you are integrating the expression dx over a constant squared plus the variable squared, then that's going to equal 1 over your constant times the arctangent of your variable over your constant. So if you look at our expression carefully, we have 49, but we would need to rewrite that as 7 squared. And that way, by rewriting it as a perfect square in that manner, we can see that our a value is just 7. In other words, our constant is 7. So this will integrate to 1 over 7 inverse tangent of our variable over our constant, like that. So now we just slap them all together. Remember, it's going to be this result minus this result minus that result. Notice the minus that we had factored out will distribute to both of those second integrals. So we now have as our final answer the natural log of the absolute value of x minus 1 minus 1/2 ln absolute value x squared plus 49 minus 1/7 arctangent of x over 7. And then don't forget your constant of integration, and there indeed is your final answer.